Okay, good morning or good afternoon, depending on when we're meeting. Once again, I have a Camtasia presentation for you, along with a PowerPoint. You should have a reference table handy, maybe some paper to write on to take notes on this. You definitely need a stylus so that you can complete the work along with me. And this is a 3-day project. These 3 worksheets are not going to be due until Friday. I'll say Friday afternoon. Oh, you know what? Why not say Monday morning? We'll say Monday morning. We'll give you a couple of days to get this done. So let's just start. So we'll be talking about writing formulas for binary compounds in a textbook that starts on section 9.1 and also goes on to 9.2. So first things to talk about is that the cation as a positive oxidation element gets written first. So whatever element is a metal gets written first. So sodium and sodium chloride is always written first, and chlorine is the anion, the negative oxidation state goes second. That is called an anion. So we also have to say that the algebraic sum of the oxidation numbers has to be 0. If you remember, or if you look at the reference table, calcium has a +2 oxidation state, and oxygen, if you look at it on the reference table, has a -2 oxidation state. Give me 1 second and I'll show you exactly what I'm talking about. We look here, -2, and calcium here is a +2. So what we're talking about are the oxidation states. What that means is the calcium has 2 electrons in the outer shell it would like to give up to get to 8 shelling. Oxygen has 6 electrons in the outer shell it would like to get 8 to have a full set. We get those numbers, the 2-8-2 from the reference table, and we get the 2-6 from the reference table too. Now, how do we show it? Well, what does this have to do with anything? Well, you have to get these 2 electrons to jump over there so that we have 8 showing in the calcium and 8 showing in the oxygen. So what we're going to do is first write the formula for calcium oxide. So the first thing we do is write CaO. I write the calcium because it's got the positive oxidation state. It's the metal. It gets written first. And I write the O as oxygen. It has a negative oxidation state. It gets written second. So I write the oxidation states as they appear in the reference table that I just showed you. You have to look at the reference table. Some of you are extremely lazy and don't want to do it. That's fine. You can get this wrong. Then I crisscross the charges. So I'm going to take the charges and write them below the symbols for each element, like so. Then I ignore the sign. So I have Ca2O2. Then, if the case is they can be reduced by the same factor, you reduce them and write it without, in this case, without subscripts at all, because I don't have to write ones. So this compound is CaO. So I crisscross the charge, write them as subscripts, and ignore the charges and reduce if possible. Here are some examples. So lithium and oxygen. So lithium has a +1 oxidation state and oxygen has a -2. So I bring this charge down here and I bring this charge down here. That makes this Li2 and this O without a number 1 written under it. So that is the symbol for lithium oxide. For aluminum and chlorine, I bring 3 down here and the -1 down here. So this becomes Al, no need to write a subscript, and Cl3. No sign is needed. So this is aluminum chloride. For the compound that is formed by iron and sulfur, this becomes, the 3 comes down here, and the S comes down here, the charge. So I write Fe, 2, no sign, and S3. And for the last one, I would write the charge comes down, the charge comes down, or the number without the charge actually. So this becomes H3N. What we're doing here is actually equalizing charge. It's saying that for this to work, for this compound to form, for every 2 lithiums, I need 1 oxygen, because the oxygen has 2 spots for electrons to land, so each lithium is going to provide those electrons. So that's why this is a 2. For chlorine, aluminum has 3 spots for electrons, which means I'm going to have 3 chlorines available to grab those 3 outer electrons, and so on. It's called equalizing charge. You really don't have to worry about it. All you have to know is to crisscross the charges and ignore the signs on the bottom. Notice I do not write the signs in the end, or the superscripts at the end. What I'm going to do is just take a quick look at, there's a worksheet, writing formulas using crisscross. Bear with me while I get to that. That's for this packet. So I will post the answers for this. I want you to get as many of these done as you can, and then you'll check yourself. Sodium has a +1 charge and chlorine has a -1 charge, so you crisscross, it's NaCl. For this one, the combination between sodium and this thing, the carbonate ion, sodium has a +3 charge, +1 charge, carbonate a -2 charge. So when I write this out, it's written as Na2CO3. For this one, combination between ammonium and sulfate, little different because it's 2 polyatomic ions joining together, and a slightly different rule. So this has a +1 charge, the ammonium. You look in the polyatomic ion table, and this is a -2 charge. I did not write the 4 down there. They still crisscross, but you have to imagine that there are parentheses around this SO4. But since it's a 1 and it's going to be outside the parentheses, I don't have to write anything. Since this polyatomic ion has a charge other than -1, I have to use a parentheses outside of the set of brackets. We'll see more examples of this as we move forward. Coming down the page a little bit, potassium and phosphate. In this case, potassium has a +1 charge, phosphate has a -3. So the crisscross is simply K3. The 3 comes down, and then the +1 would be outside the PO4, PO4. Potassium nitrate. Potassium has a positive 1 charge, nitrate has a minus 1 charge. When I crisscross that, that comes out here. There's no need for brackets. Over here, this becomes a 1 when it comes down. There's no need for brackets there. For this example, calcium and sulfate, if you look, calcium has a positive 2 charge, sulfate has a negative 2 charge. This is kind of like the calcium oxide example that we started with. You have to bring the charge down, use a bracket outside the polyatomic ion, just to show me that there will be 2 of these things needed. And then this 2 from the sulfate, the negative 2 from the sulfate, comes down for the calcium. Since I have a negative, I have a 2 outside of as a subscript for the calcium, and a 2 as a subscript for the sulfate. They cancel each other out, and I simply write CaSO4. I want you to practice them. Try to do all of them. An answer key will be posted for you to look at. So, back to this. Naming binary compounds. Now, there is a link that shows on this. That link is also in the assignment page so that you can watch this separately. So this is easy. Everybody should be able to get this. Very easy. When you have a binary compound, the symbol for a binary compound, and you're reading it, we should not be reading NaCa as NaCl and CaO as cow and ALF as ALF. We do not sound these out. We're using the symbols to give us the names. The element with the positive oxidation state, the metal, gets listed first. It keeps its regular name, whatever is in table S. The second element gets IDE added to the last syllable of its name. So, sodium chloride, sodium and chlorine become sodium chloride. The ene becomes an ide. That IDE is a way of saying that it's now joined together. It's almost married. Calcium and oxygen joining together form calcium oxide. Gracie's coming in to say hello. She's wondering who I'm talking to. Calcium oxide, the GEN becomes an IDE, telling me that it's joined a compound. The next one, excuse me, aluminum and fluorine joining together become aluminum fluoride. No longer aluminum fluorine, it's married. It tells me that it's part of a compound. So at this point, you should probably stop this video where we are here and go to the chemistry website. The link is in your assignment page, and watch this. I'm going to go to the sheet, complete the worksheet naming ionic compounds in a second after the next slide, because it kills 2 birds with 1 stone. So the next page, again, it's naming compounds with polyatomic ions. You would go to the chemistry page to look at that too, or to see a lesson on it, and then we'll talk about this worksheet in a second. So we've talked about polyatomic ions already. Now we want to see, how do we name things that have polyatomic ions associated with them? Well, the one thing is, and you may note this, if there are more than 3, go to E. If there are more than 3 elements in a compound, go to table E. Chances are there's a polyatomic ion associated with it. and you should be able to identify it. So, the first one is calcium, and that is attached to, according to reference table E, I'll give you a second to look it up. Actually, I will bring it up myself. You can see here that's sulfate, so that is calcium sulfate. Go back into this, Na3PO4. That should be fairly easy to do. I know Na3 is sodium, but the PO4, let's see, is that listed? PO4, let us see, Mr. Chowsky, where is PO4? Oh, there's the PO4, phosphate. So that compound must be then sodium phosphate, and so on. So this is iron. Which iron, we're not quite sure yet. We haven't talked about that, the stock system. This is iron. I go to the table, I look up, and that should be nitrate. So iron nitrate. This one has 4 elements in it. So this is 2 polyatomic ions joined together. And I look this one up. I'll go quickly. We'll look at that again. That is NH4 and CO3. So NH4 is here, ammonium, and CO3 is below it. So that compound is called ammonium carbonate. That should be fairly easy. CuSO4 is copper, and the SO4 makes it, you saw it before, that is sulfate, again in table E. This one would be aluminum. We saw this one before, phosphate. And this one, NaHCO3, should be HCO3 we haven't seen before, so let's go search for it, see if we can find it. HCO, hydrogen carbonate. We've seen this chemical in lab, NaHCO3, sodium hydrogen carbonate. The other name for it would be baking soda, the more common name. So there are examples. If you go to the chemistry page at this point, once we finish watching this, you should go and watch him explain how to do problems naming polyatomic ions. I am going to go so you should stop this, watch that, then come back, and there is a worksheet called Naming Ionic Compounds that I'm going to go to quite quickly here on my whiteboard. And I had some of them already filled out, some clues filled out for you here. So I don't know why I did that. So to make this a little bit easier for you on this page, naming ionic compounds, if it's highlighted in yellow, that is something that is in table E. You should look those up. If it is highlighted in pink, that is going to be the next slide that I talk about. And that is using the stock system. So let's just talk about this first compound. That would be calcium and carbonate when I write it out. This next one would be potassium, and it's no longer chlorine, it's chloride, IDE. This would be lithium. Now, normally that would be bromine, but it's married to it. It's a compound now, so that would be lithium bromide. bromide. And number 5 would be magnesium, not chlorine, because it's married to it now, magnesium chloride. Okay, so let me go back to the PowerPoint and take a look at the next page, which is why the things are highlighted in pink. So some elements, your transition elements, have more than one oxidation state, and the way that we designate that is by using Roman numerals. And when we do that, we have to keep in mind we don't want to use Arabic numerals, the regular 1, 2, 3, 4 anymore. We want to use Roman numerals to tell me which oxidation state of the element am I using. So iron oxide, there are two different iron oxides. I can have iron 2 oxide or iron 3 oxide. Now, I'm going to jump quickly to the reference table to show you what we're talking about. Look at iron here. All of these transition metals have multiple oxidation states. You have to be able to indicate which one you're talking about, which one is in the formula, because it makes a difference. So subscripts make a difference, as we said earlier a few days ago. So iron 2 oxide, the way that we would write this out as a formula is Fe, it's an E, plus 2. They're telling me to write, instead of a Roman numeral 2, a plus 2 is how we write it. And then oxide. And I look up oxygen's oxidation state. Just going to show you for this one. I know this is redundant, but that's oxygen has a -2 oxidation state all the time. -2. I do the crisscross, and I end up with Fe2O2. But if you remember, we said those can reduce. So instead of writing Fe2O2, I write FeO. Now for iron 3 oxide, now I'm going to erase this just so that it's not as. For iron 3 oxide, I write F F E plus 3 O, that should be a 3. I have COVID head, Fe3O minus 2. Now I crisscross. So the 2 comes down here and the 3 comes down here. The order of that really doesn't matter. And I'm just going to use this to erase this. Those are gone, and my final answer is Fe2O3. I do not have to reduce this. The difference is this iron oxide is the ore. This is ore. This is what comes out of the grain, the ground. And this iron 3 oxide is rust. Two very different things. We're not going to worry about nitrous oxide. So let's go back to that worksheet. Actually, let's jump. And let's look at this last one. Writing formulas using the stock system. So Fe, I know that iron has a +2 charge here. Oxygen always has a -2 charge from the reference table. I do the crisscross, and it's going to end up with a 2 down here and a 2 down here. I know that I can reduce those, so I'm simply going to jump ahead because I'm smart now. And I'm going to write FeO. This one is Fe plus 3O minus 2. I do the crisscross, and that becomes Fe2O3. No need to write that anymore. Copper 1 hydroxide. Now hydroxide, keep in mind that hydroxide is a table E. At this point, you should have some idea which ones are table E. So this is Cu plus 1. Just write a plus. Hydroxide is OH, and that has a minus. So since these are both going to be ones that come down, we simply write this as CuOH. So that's copper hydroxide. Copper nitrate. Copper nitrate is, copper nitrate is, that's Cu2. So which form of copper? It's Cu plus 2 nitrate polyatomic ion. Go to table E. It is an NO3 as a -1 charge. Now I want to crisscross these. Because this is a 2 with the copper and it's coming down to a polyatomic ion, I have to use the parentheses that I showed before. So this will be, and this is a 1 that will come down to the copper. So this is a CuNO3 taken twice. This is copper nitrate taken two times. And this last one, tin 2 carbonate, SN, stock system, plus 2, which type of tin? The one that where 2 electrons have been lost. Carbonate, CO3, that has a -2. Well, since this 2 will come down outside the carbonate and this 2 will come outside the tin, we can reduce, and we don't have to write any brackets or anything. We simply write this as SnCO3. So I can erase these. I never write the charges with a completed compound. So SnCO3 would be your final answer for that. So let me just go to the tables here again, the questions, and show you how we would approach those. You can go back and watch any of these review sheets fairly easily. So if it has yellow, if it has pink, that means it's the stock system question. That's a transition metal. So we have to figure out which transition metal was it. Well, if I look at this, that's it. Right now, it seems like the subscripts are 1s outside of the iron and the sulfate. But the sulfate has a -2 charge. So this had to have a -2 charge. So for that to balance, that had to have a +2 charge. So this would have to be, we would write that out, iron, Roman numeral 2 in brackets, sulfate. I get that from the table. Number 6, transition metal. I kind of do a reverse crisscross here. Well, what is the oxidation state on iron? Well, it had to be a 3 since there's a 3 down here. So this was iron, Roman numeral 3, and there had to be, for the chlorine, it always has a -1 oxidation state, and it's married, so it's called iron 3 chloride. Let's take a look at a few more examples of these. So this is, both of these are polyatomic ions, no problem. This should be straightforward. Number 7, look at whatever element that is in the polyatomic ion. 8 is 2 polyatomic ions, you just name them both. Aluminum only has 1 oxidation state, and then whatever the polyatomic ion is in yellow. Number 10, we have an example of one with multiple oxidation states, a transition element with whatever this thing is. So, easy way to do it, Cu is copper. I know that because I know what Cu is. I don't know which oxidation state I use, so I'm going to leave room for parentheses here. And then whatever this thing is. Remember, 3 or more, go to table E. So that is called an acetate ion. And an acetate ion has a charge of -1 when I look it up in the reference table. So this had to be, for these to, if this is a -1 on the reference table, this had to be a +1 to cancel it out. The ions balance each other. So this is copper 1 acetate. And the last one here, I'm going to let you try the rest on your own for this. This is lead Pb, but I don't know which form. So this is lead. I'm not sure which oxidation state. So I'm leaving a bracket. The SO4, more than 3. This is where you have to be careful. Let's see, lead. SO3, let's see, SO3, it says it has a -2 charge, and that's called a sulfite. So coming back to that one, that's lead sulfite. If that's lead sulfite, that means that this had a -2 charge, so this has to have had a +2 charge to balance out. So I put a Roman numeral 2 there. Again, the rest of these are the clue is polyatomic ion is in yellow, and the pink means that it's a transition element. You should leave room for a bracket. Okay, so I think that more or less covers everything. Please take a shot at those 3 tables. Those are not going to be due until Monday. If you don't finish them the first day, try again. I think on Friday I'll try to do a live Zoom with each section for anybody that has any trouble. And I'll let you know more about that as we move forward. So I hope that helps. Do watch those embedded videos. It's there to help you. Thank you.